Hope you feel like doing proofs. We're going to do the FTLI proof. It doesn't take long. This is really right out of the book, but I'm going to lay it out in a way that I hope makes sense. We're doing the integral over C of gradient f dot dr. And that's equal to, from A to B, remember what C is. C is some kind of curve, that's R of T between A and B. We're going to substitute R into gradient F. And all it means is just, well, we got a parking space for it. So R goes in there, and it's still dotted with R prime dt. Now let's write down the big idea. This can be rewritten because we know what the gradient looks like. It's the integral from A to B of the partial of little f with respect to x dotted with dx dt plus the partial with respect to y dotted with dy dt plus the partial with respect to z if we went into 3 dimensions times, really, not dotted, but dz dt on the end. And here's the big idea. Do you remember doing chain rule where we're going to take the derivative, like in this case, f is a function of x, y, and z. But x, y, and z are all functions of t. So if we want to take the derivative of f with respect to t, we have to have the contribution through x, contribution through y, contribution through z, and they're added up. So this is literally chain rule, the multivariable chain rule, for exactly the following. It's the integral from A to B of the derivative with respect to t of f of r of t. It just so happens that the gradient works out to match what we would do if we did this derivative, where f was a function of x, y, z, and I was going to do this. Well, if you're going to do the derivative with respect to t and then integrate with respect to t, these two undo each other. So that's fundamental theoretical calculus part 1. So you end up with f of r of b minus f of r of a, which is the last part of the fundamental theorem for line integrals. So that's not much of a proof. It's pretty easy. Let's take a look at an example so you can see how these pieces actually happen. Let's do a quick example problem. Because it's one thing to say, oh, it's chain rule and everything there is perfectly cool. That's another thing to actually see an example when you're looking for that chain rule to happen. So I made up a quick example for you, and it looks like this. I'm going to have f of x, y, z is known to be xy plus xz squared. So it's very simple. I'm going to take for my r of t, I'm just making this up, sine t, cosine t, e to the t. So now if I do the derivative with respect to t of f of r of t, if I do that, that's going to be the partial of f with respect to x times the derivative of x with respect to t plus partial of f with respect to y times the derivative of y with respect to t plus partial of z, partial of f with respect to z, derivative of z with respect to t. That's chain rule, just reviewing that idea. Now let's compare that to what I'm about to write down. I'm going to need the space for it. I think I can squeeze it in here. All right, so I'm going to have integral from A to B. Well, remember, this is the line integral, so we're doing the C grad f dot dr. Is it dr? Is that how they write it? Yeah, that's how they write it. So we're going to do that, and that's equal to integral from a to b. And now it's going to be gradient of this, because that's supposed to be the integrand. So I'd have y plus z squared, comma, x, comma, 2xz, dotted with, and I've run out of space on the camera, I'll just write the dr over here. Dotted with the derivative of this thing. It gets really long. It gets long and crazy looking, but let's take a look at what it's going to look like when I put all the pieces together. So I'm going to go back this way now. If I have this thing and I do all the dot stuff and the substitution, so this is substitution and the dot, I get the following. It's the integral from a to b of, and you can do this yourself, big old bracket, I'm going to get cosine t plus e to the 2t times, those two times cosine t, plus, next up is going to be sine t times negative sine t, plus 2 sine t e to the 2t. Close off that big bracket dt. Now let's just look at these pieces here. That's going to be the partial of f with respect to x with the pieces substituted in, times dx dt. That's going to be the partial of f with respect to y times the dy dt. So this is after you do the substitutions. Everything matches up. Everything's where it needs to be. It's just the chain rule again. You see these plus signs? It's these plus signs. And all the pieces are there. You just do the substitution. Well, like we saw in the proof, I'm going to be integrating this, and now I see what it is. It is the derivative of f. It's this derivative. I'm going to be integrating that derivative dt. So I'm going to get this thing. I'm going to get that for the answer. It doesn't matter what this mess looks like. You don't have to worry about, oh, but we have to go term by term. No, we know what's going to happen. I know a formula where it comes from. So I don't know if that proof makes sense to you. I hope it does. Hope it does. Knowing where the stuff comes from is the key idea. All right, I've also got a quick proof of Green's theorem, and the book is right. The actual proof of Green's theorem has a wrinkle to it that the book doesn't focus on. They do one simple piece, and then they leave it up to the professor what they're going to make out of it. So let's take a look at the complicated bit of Green's theorem. Green's theorem, if you remember, is you got to have this is the symbol for a line integral over a closed curve. So there's that. And I'm going to have p dx plus q dy, and that's equal to the double integral of d over qx minus py dA. So that's Green's theorem. The proof for this leaves off an important idea. Your simple closed curve C could be kind of lumpy. This could be C. It has to be oriented counterclockwise. One of the things you can do is you can say, okay, let's cut it straight across here. Let's say we cut it straight across there. Now, you can do oriented this way and then back around this way and apply Green's theorem to just this little piece here. Then let's do the rest of this piece. If I did this piece, I'd be going along this way, and I'd come down here, and I'd go back along this zipper. So the big idea is, when I integrate in this direction, I'm going to get the same answer as I get in that direction, except for opposite signs. So I can take what started out as a fairly lumpy, messy domain, a curve like this, and I can say, well, you know, I could do it like this, I could do it like this, I could cut it this way, and now this little piece has it both ways, this little piece has it both ways, this little piece has it both ways, and I can do the computation for this, the computation for this, the computation for this, computation for this on their own. And these places where the pieces, the next door neighbor pieces are glued together would cancel out. So you're just doing the integral over the whole C, and the rest of it doesn't contribute anything. The rest of these little zippers are gone. So to apply that idea for the proof of Green's theorem is, well, let's just take C to be this then. What if this is my C? Well, there's actually three pieces to it. There's C1, C2, C3, C4. There's a lot going on there. But remember, I could have had one of these pieces be curvy, and it doesn't really matter. The book does a piece where a couple of parallel sides are kind of curvy, and it doesn't matter. But if we do this as the C curve, and then that's the D inside, we can see the following things happen. We're going to do it one piece at a time. Let's do the P stuff first. So when I do this P thing, this P piece turns into the integral from A to B of, oops, not A to B, it's going to be C1, because it's got dx going on it, and that's going to be my P of x, and I'm going to call this curve G1. So the curve for C1 is G1. So it's x comma G1 of x plus, and there's going to be a negative here for the C3, because I'm going against the orientation of the number line. See how C1 goes with the orientation of the number line? C3 goes against it. So even though I have the same starting and ending points, I have A to B, let's say A to B, this guy goes from B to A. Do you see? So if I'm going to have these guys match up, if I'm going to have this B from A to B, I need a minus sign on this guy. And this guy here is going to be P of x comma G3 of x dx. So that's just this P piece being rewritten. So I've got the substitutions in there. It's going to be they're both going to be from A to B. Let me erase those C1s and C3s. They're both going to be from A to B. And then what happens is, if we look at just the py piece here, so I do the double integral over d of negative py. Let's do this dy dx because of these two y's there. And then if I do this, I'm going to think of this problem now with a box going this way. So it's going to be the top curve, which is G3. Bottom curve is G1. That's from C3 and C1. And then I'm just going to go from A to B. And what happens is, I can actually do this integral. I'm going to have the partial of P with respect to y dy. So this is going to be regular P. So I'm going to get the negative P. Still got to integrate it from A to B. And it's going to have the dx on the end. But on the inside is G3 of x minus P of G1 of x dx. And when you do this step, distribute this minus sign, it's going to match exactly this. It matches that. But here, throw an x in here and an x in there. There we go, for substitution purposes. So you've got the situation, x G1 minus, or sorry, P of x G1 minus P x G3. And here we've got minus P x G3 plus P x G1. That's a G1 right there. So it's the same. The P stuff matched up. Now, here's what's going to happen with the Q's. The book skips the Q case, but the Q case is, let's just do the setup for you so you can see what's going on. When you go to do the Q case, a funny thing happens. The minus sign that we needed on the P, we don't need on the Q. It's very funny, and there's a reason for that. The reason we don't need the minus sign on the Q is because it just turns out that when we go in this direction, counterclockwise, we do top curve minus bottom curve, but the top curve is in the opposite orientation of the number line. Now when we do dx dy, you have this box here, and look, C2 is now the top curve. The lower number curve is the top curve. Here, the higher number curve is the top curve. So the P needs a minus sign to get the subtraction to be in the right direction. The Q doesn't. That's why the Q doesn't get this extra minus sign. Isn't that weird? And that's why there's a minus sign in Green's theorem. Is because in one direction we do dy dx in the proof. The other one we do dx dy, and it turns out the dx dy doesn't need the extra minus sign. So when you do the Q piece, you're going to have from, let's say, C to D. Okay, so, sorry, C to D. Go from C to D. So I'm going to have C to D, and you know what's going to happen here. You're going to have Q of, and let's call it X, and God, I gotta give these things a name. This is G2, but it's really G2 of Y. Because X doesn't change. We're going straight up. X doesn't change. And it's going to be minus Q of G4 of Y dy. That's what's going to happen over here. Now, if I take this piece, the Q X, so I'm going to do double integral. I've got partial of Q with respect to X. Let's do it dx dy. Because I know what to do with Q sub X and dx first. But if this is X equals, I need X equals. So X equals top curve, sorry, wrong. I need X equals top curve minus bottom curve. So it's going to be top curve G2, G4. And that's the big difference with the one we just did. This time the top curve is the lower numbered, and the bottom curve is the higher numbered. So if I do that, and then this goes from C to D, you can see what's going to happen. I'm going to evaluate, I'll get the Q's. I'll get the Q of G2, sorry, Y G2 of Y minus, and I still got to do the integral from C to D, Q Y G4 of Y dy. So I've got the G2 minus G4, Q of G2 minus Q of G4. So they match. And what's cool is we don't actually even finish doing the integral. So that's proof of Green's theorem for just a box. But the idea is any other kind of shape for C will work because you could make these cuts and have pieces of it that are amenable to the proof. So the proof would hold for the pieces, sew the pieces together. The little seams where they would sew together would cancel out. So all you do is evaluate along the boundary, which is what it's saying. Evaluate along the boundary is the same as evaluating over the region. That's what Green's theorem is proving. All right, you guys, have a great Thanksgiving. Get some sleep. Keep doing your math.